Voice over Wi-Fi, Why Calls Fail. A mini-course focused on the RF fundamentals, explaining how interference, coverage, and Wi-Fi configuration impact call stability and voice quality. Mobile voice has evolved from traditional circuit-switched networks to fully IP-based solutions. Today, voice is transmitted as data packets over different radio technologies, where RF and quality of service mechanisms affect quality and reliability. In 2G and 3G networks, circuit-switched voice use dedicated radio channels, providing predictable and stable performance. In 4G, voice over LTE delivers voice as IP traffic over licensed spectrum, using centralized quality of service mechanisms to ensure high reliability. Voice over NR in 5G further improves performance through lower latency, advanced scheduling, and enhanced interference management. Voice over Wi-Fi, in contrast, operates in unlicensed spectrum. Because Wi-Fi lacks centralized radio resource control, voice performance is more sensitive to interference and lack of end-to-end quality of service. Voice over Wi-Fi enables mobile calls over a Wi-Fi network, often used in facilities with weak cellular coverage. It can work well in environments with few nearby Wi-Fi networks and limited interference. However, Wi-Fi was not designed for real-time voice and operates in half-duplex mode, meaning devices cannot transmit and receive simultaneously. This creates limitations that can result in reduced call quality, dropped calls, or missed calls, especially in congested environments. In business settings, the challenges are greater. There are typically many users with smartphones, active mobile hotspots, and other devices transmitting on Wi-Fi frequencies, along with numerous hard-to-control variables. The main source of dissatisfaction is recurring audio and quality issues that cause repeated service disruptions. Although many telecom operators initially launched voice over Wi-Fi to improve indoor coverage and enhance the user experience, fewer operators actively promote or expand the service today. The main reason is performance variability. Wi-Fi technology can be the limiting factor, and operators have limited control over customer-managed Wi-Fi environments. When audio quality issues, dropped calls, or unstable performance occur, they generate high volumes of support cases that are difficult and costly to resolve. Because many of these issues originate outside the operator's network, troubleshooting becomes complex and inefficient for commercial 4G and 5G providers. As a result, some operators choose to limit or avoid large-scale voice over Wi-Fi deployments until Wi-Fi standards and performance become more predictable and robust. Wi-Fi operates in unlicensed frequency bands, 2.4 GHz, 5 GHz, and 6 GHz. Because these bands are unlicensed, they are not reserved exclusively for Wi-Fi. Instead, they are shared with many other wireless technologies, including mobile hotspots, Bluetooth devices, IoT equipment, microwave ovens, and various consumer electronics. In environments with many users and devices, these shared bands can become heavily congested. Multiple devices and access points may operate on the same or overlapping channels, leading to co-channel and adjacent channel interference. Since Wi-Fi channels overlap, spacing between channels is necessary to minimize interference, which limits the number of channels that can be effectively used. The 5 GHz and 6 GHz bands offer more available spectrum and generally less interference. However, higher frequencies have a reduced ability to penetrate thick walls and obstacles, often requiring a denser deployment of access points to ensure reliable coverage. Wi-Fi works much like Ethernet over the air, but with lower capacity. Transmission and reception take place on the same carrier frequency, using a protocol-based access method. This means Wi-Fi operates in half-duplex mode, devices cannot transmit and receive at the same time. Before sending data, Wi-Fi devices must first check that the channel is free. Only then can they transmit. Even with technologies like MU-MIMO, only a limited number of devices can send or receive simultaneously, and still only in one direction at a time. When many users share the same frequencies, capacity becomes limited and interference increases. For voice services, this is critical. If packet delay exceeds roughly 150 milliseconds, users may experience echo or noticeable audio delay. Even with echo cancellation, the conversation can feel unnatural or lagging. Wi-Fi versus mobile networks, capacity and delay. In simple terms, the more devices connected to a Wi-Fi network, the more interference and competition for airtime. This reduces available bandwidth and increases delay per packet. With only a few active devices, voice over Wi-Fi can perform well. However, as more devices compete for the same channels, interference increases and network capacity decreases, directly impacting real-time voice performance. In contrast, 4G and 5G mobile networks operate in full duplex, using separate carrier frequencies for transmission and reception. Operators also control and manage licensed spectrum, enabling structured capacity planning and more predictable performance. This fundamental architectural difference explains why Wi-Fi can struggle to deliver stable, real-time voice quality in busy environments compared to 4G and 5G. One key limitation of voice over Wi-Fi is the lack of true power control mechanisms in Wi-Fi technology. Wi-Fi does not provide continuous uplink power regulation in the same way as cellular networks do. Within the specifications IEEE 802.11, there is no dynamic transmit power control implemented at the MAC or packet level. Power adjustments are limited to static or semi-static transmit power settings and basic radio interface adaptations. There is no closed-loop power control between endpoints during an active voice session, and no per-packet optimization for voice traffic. This is true limitations. As a result, Wi-Fi operates on a best-effort basis in unlicensed spectrum, where performance depends heavily on surrounding interference and overall network load. Because there is no continuous regulation of transmit power during a call, voice quality can fluctuate. This may lead to unstable audio levels, distortion, packet loss, and call dropouts. The absence of dynamic, continuous power control significantly limits the ability of voice over Wi-Fi to deliver the same level of clarity and stability that cellular 4G and 5G networks do, where power is regulated throughout the duration of a call. Quality of service limitations in voice over Wi-Fi networks. Providing reliable quality of service for voice over Wi-Fi traffic is complex and difficult to guarantee. Effective IP quality of service, VLAN tagging, or traffic prioritization on handheld Wi-Fi devices requires advanced configuration, compatible software, even in Wi-Fi 6 or Wi-Fi 7 devices. Most smartphones do not have full control over Wi-Fi level quality of service mechanisms. In iOS and Android-based devices manage traffic internally and may restrict from controlling low-level quality of service parameters where voice packets compete with other application traffic within the device before even reaching the Wi-Fi interface. Without consistent configuration throughout the network, voice traffic cannot reliably be prioritized over other data traffic. As a result, voice over Wi-Fi largely operates on a best-effort basis. Roaming limitations in Wi-Fi networks. Roaming between APs in Wi-Fi networks is not always seamless or guaranteed where they support coordinated roaming. In voice over Wi-Fi solutions, the active voice session remains connected to the current AP until the signal becomes too weak. When the signal drops below a certain threshold, the call may disconnect before the client device searches for and connects to a new AP. For seamless roaming to work properly, overlapping sessions must be handled during the transition between two APs. This requires advanced Wi-Fi controllers, properly configured access points, client devices, and/or smartphones that support fast roaming protocols. Technologies such as MAC cloning can be used to assist roaming, but this will impact overall Wi-Fi network capacity and performance. Dropped and missed calls in voice over Wi-Fi networks. Due to the inherent limitations of the voice over Wi-Fi architecture, Wi-Fi networks cannot provide the same level of service quality and availability as licensed 4G and 5G networks. Consequently, users may experience dropped calls, degraded voice quality, or calls being redirected to voicemail. Voice over Wi-Fi is highly sensitive to performance variations and inherent limitations in Wi-Fi networks, including unstable connectivity, SIP registration delays, non-seamless handover, network congestion, and radio interference. In contrast, 4G and 5G networks use centralized radio resource management, fast handover procedures, and bearer-level quality of service mechanisms to ensure controlled latency and prioritization for voice services. Indoor cellular coverage can be improved through the deployment of distributed antenna systems (DAS) with repeaters or small cells, while maintaining full integration with the operator's core network and end-to-end quality of service framework. Do Wi-Fi 6 and Wi-Fi 7 improve quality of service? In general, Wi-Fi 6 and Wi-Fi 7 do not change how voice-over Wi-Fi works at the protocol level. Voice-over Wi-Fi still uses SIP, RTP, and IPsec to the operator's core network. However, these newer Wi-Fi standards significantly improve the radio performance, which to some part impacts voice quality. Wi-Fi 6 introduces more efficient spectrum usage and better handling of multiple devices, reducing latency, jitter, and congestion. Wi-Fi 7 improves reliability through technologies like multi-link operation, MLO, which enhances stability in busy environments. Voice-over Wi-Fi performance still depends heavily on proper network design, quality of service configuration, and roaming setup. Wi-Fi 6 and 7 helps, but configuration and deployment quality remain critical. Future GAN and Wi-Fi 8. In the coming years, possibly well into the 2030s, Generic Access Network, GAN, will evolve as a unified service framework. GAN represents a flexible approach to connectivity, where access technologies can be seamlessly integrated services over Wi-Fi 8, 6G, fixed access and other technologies. Wi-Fi 8 is in early stages but anticipated to focus on improving reliability, latency, and performance rather than only peak data rates. Wi-Fi the 8th of May introduced the foundations for full duplex operation, but widespread adoption will depend on technological maturity, cost efficiency, and power optimization. In practical terms, this means that voice services would no longer be tightly bound to a specific access technology. Instead, various network types could be used interchangeably and transparently for voice communication. In this context, voice-over Wi-Fi would evolve into a fully established and naturally integrated voice service, rather than a supplementary feature. Summary: VoIP versus VoLTE versus VoNR. RF-based voice services are delivered via voice-over Wi-Fi, voice-over LTE, for GLTE, and voice-over NR, 5G NR. All three protocols are IP-based solutions built on the IMS core, but they differ in access technology and user experience. Voice-over Wi-Fi uses a local Wi-Fi instead of the cellular network, making call quality dependent on the performance and configuration of the Wi-Fi environment. Voice-over LTE is a widely deployed solution that provides stable performance, reliable mobility, and consistent voice quality under operator control. Voice-over NR represents the future evolution of mobile voice, offering improved efficiency and lower latency compared to LTE. Its availability depends on the rollout of future 5G standalone networks. Handover between them is standardized within 3GPP specifications. Although all three services are based on IMS, their roaming availability varies. We believe that voice-over Wi-Fi can be a suitable solution for many users, particularly as it is often considered a cost-effective option. However, based on our experience, this type of solution is primarily adopted by private individuals. Businesses and enterprise customers typically cannot accept the limitations and performance constraints associated with voice-over Wi-Fi. It is likely that voice-over Wi-Fi will evolve into a fully functional and seamlessly integrated voice solution in the early 2030s. This development will largely depend on advancements in future Wi-Fi standards, particularly the maturity and widespread adoption of the Wi-Fi 8 specification, which is expected to introduce improved determinism, lower latency, enhanced reliability, and better support for real-time applications such as voice. A summary of voice-over Wi-Fi limitations. Wi-Fi is inherently limited by the characteristics of IEEE 802.11 networks and therefore cannot provide the same level of reliability, service continuity, and performance as 4G and 5G cellular networks. Wi-Fi operates in unlicensed spectrum, half-duplex, and relies on contention-based medium access, making it more susceptible to delay, interference, congestion, and fluctuating signal strength. As a result, voice sessions are sensitive to latency, jitter, and packet loss, which may lead to degraded audio quality or dropped calls. In addition, Wi-Fi roaming does not inherently support seamless, deterministic handover comparable to cellular mobility procedures. Delays related to Layer 2 roaming, authentication, IP address renewal, and SIP or IMS registration can interrupt active calls or cause missed incoming calls. Temporary loss of connectivity or instability in the Wi-Fi environment may also result in calls being redirected to voicemail. Voice over Wi-Fi performance is influenced not only by the quality of the Wi-Fi network but also by limitations within smartphones themselves. Device hardware characteristics such as antenna design, chipset capabilities, and power-saving mechanisms can affect signal stability and roaming behavior. Variations in operating system implementation, Wi-Fi driver performance, SIP and/or IMS client integration may lead to registration delays, slower call setup, or interruptions when transitioning between Wi-Fi and cellular networks. In addition, background traffic management and battery optimization features can negatively impact voice session stability. Addressing these limitations requires improvements at both the device and standards levels. Enhanced Wi-Fi chipsets with improved roaming intelligence, more effective power control mechanisms, tighter integration between the Wi-Fi stack and IMS functionality, and support for low latency, deterministic Wi-Fi features will be essential. Continued evolution of Wi-Fi standards, combined with optimized smartphone hardware and software design, is necessary to achieve more reliable and carrier-grade voice over Wi-Fi performance. Before you go, don't miss what's coming next. At Weisenfeld Tech, we are building a growing library of high-quality technical microcourses, delivered through modern e-learning. The courses are free, short, practical, and designed to create real value. On our YouTube channel, we will continue to explore many smaller technical topics. Areas that both beginners and experienced technicians often find interesting and useful from a technical perspective. By subscribing, you'll get access to new content as soon as it's released and be the first to discover upcoming microcourses. Subscribe to our YouTube channel today and explore more at www.weisenfeldtech.com. We look forward to continuing the learning journey with you.